How's it going, everyone? Welcome. Eulier Gonzalez here. And today is might be set the precedent of what's next, especially in since right now I'm living in Argentina and we'll experience this an economic boom by normal people, the middle class can have access to credit and that kind of stuff. It seems that that is now over, or at least that's the signals that I can find and other analysts can find in the banking industry, right? In the loan market. So, but in any case, this is also the reason why I'm recording this series of videos, and specifically this as a way to now finally uh, read about this the scope of JavaScript, what is a scope in JavaScript, so we can solve these problems once for all, and we can provide our services across the internet, and therefore now have the opportunity to capitalize ourselves in this particular system, right? Despite that, we are not going to have access to credit. This is not the end of the world, all right? But credit help you, especially if you want to, if you have an idea to set up a business, or if you now are uh, in a place where you want to move out, you want to buy your first home, so on and so forth. So, in any case, um, because in today's video, I want to read about what scope is, especially in JavaScript, right? Because here we look at the Get Started book of this series of book that you don't know, GS Jet series, where on the first book we went through describe is what is JavaScript, okay? So what is JavaScript? Who makes that? Why the name of that? Who owns the legal trademark? Who oversees the spec? What the spec says? And because we can now run this particularly language in several environments, uh, and the spec actually describe what the engine will what the language should do, okay? And because this engine, as I mentioned, it can run in different places, so the client, or the browser, or the server, light bulbs, robots. The only reality that matter for the spec is the web, okay? And because the TC39, which is the commit that oversee the spec, they don't want to break the web. Um, they provide this backward compatibility, and also something that in the JavaScript community we have, which is this polyfills. So logic that define is how these new features, if those browser doesn't support, well, must go, right? And or must use with. And also to understand that what are the different approach that we can go with JavaScript based on the experience of hundreds of programmers in computer science that we can do in order to solve problems that are relevant to computational calculations. So, for example, using the functional programming, and what are the different patterns that we can have in there, all right? Whether it's the high order functions or pipe and composition and currying, among others. And what are the set of rules that we must set abide in order to, anytime that we need to deal with these computational problems, this computational requirement or calculations, hey, we actually can follow is this particularly practices, right? But if we need to cooperate, we need to collaborate. If the problem is cooperation and collaborations, well, the object-oriented programming has shown that is somewhat a particularly good approach. Okay, and the other is the procedure. So also in that we describe is how the JavaScript engine works, all right? If this is an interpreted or a compiled language, but in essence, if not in practice, the JavaScript is a compiled language because the way how it handles errors, which is something that compiled language have that particular way of doing that, which is something that we're going to describe a little bit here on how that works. And also because the concern around the JavaScript, I say, hey, is JavaScript fast enough? There has been a good precedent, for example, in ASM, which is a subset of JavaScript, ASM.js, a subset of JavaScript that Mozilla engineers back in 2011, 2013, they poured out these Unreal game engines to the web at full 60 FPS, uh, which by providing its hints to the JavaScript engines and not to do some optimizations, they were able to do that. And then years later, with WebAssembly, uh, now again, Mozilla Engineering's they say, hey, let's go to now get rid of the parsing phase, okay, by having is this intermediary representation of the language that look like an assembly, okay, where we can now use that as as a universal compiler target. So whatever code you have written in Java, Python, C, C++, on any other language, Rust, that's going to now compile that into this WebAssembly. And when the compilation happens, which is again something that we're going to discuss in today's video, uh, that's usually now uh, transformed into an abstract syntax tree and then into a final output, which is this binary representation that is ready to be executed by the machine, right? In that particular distribution. So, for example, those binaries are, or those binary can be in Linux distribution. There is a myriad of Linux distros, whether it's on a Windows, so for example the .msa or the .exe or the in iOS, for example .app or .ipa, for example in the iPhone, okay. But this is the reason of why why WebAssembly is not only the spiritual successor of ASM, but it's also the reason why they do that in order to make now this particularly language called the WebAssembly portable and can be now run in any of these web assembly environments. This may go beyond the JavaScript scope, but at least is to understand now these particular fundamentals of the language, of how now language are processed by machines. Again, something we're gonna see in this video. We also look about the strict mode, which is a set of guidelines that developer must do to let the JavaScript engine to provide to have a good chance for the JavaScript engine for optimizing and running our code. So, the chapter 2 we look at the serving JavaScript, right? Is to say, hey, how JavaScript see a programs? What a program is? What is the thing that makes programs? Values, and what are the different type of values that we can have? So primitive and objects. And some of these primitive actually follow now is some spec, string and numbers. uh, and what these objects looks like, all right? Which is just a way of how can we organize our data, whether it's like a spreadsheet where you have one column and the value, all right, known as a hash, or you have is now a collection of values as an array, or you have now a functions as value. So because now functions are values here in JavaScript, well, uh, not only it unlock is different patterns, the functional patterns that we can go with, all right, but also is that this function as a value, it unlock also is uh, something interesting, which is that we can now is not only represent values as literal, but also held that inside of the container. Containers like variables. So variables have different syntax form, var, let, and const. Each one of them has their own particularly behaviors that indicate is how widespread this container can be have access through, all right, in our application, in our program, right? So uh, these containers, uh, we can not only define it as any of these variables, but also we can define it as a function definition, all right? And inside of the function body, we can define as variables as well as parameters. And then the other places in our programs using the try and catch. You want to now run code synchronously and to see if that actually throws now an error. So all of this is just to understand now this particular concept of variables. How can we define and use? And when it comes to the look at how functions now work in the language, whether it is as a mathematical definition of a function or as a procedure, all right? We also look at how can we use this function, which is a set of instruction at the end of the day, okay? And contain them into these variables. So anytime that we need this set of instructions to run, well, we just only have call as a reference. And calling that as a reference, or when you are now assigning a value to a variable, or you pass that value around, the way how this works in JavaScript is as a copy for primitive or as a reference for object, which is just exclusively to JavaScript in itself. So other programming language, you can define how you're going to assign or pass a value, but in JavaScript is based on it is a value type. So also we look at how you can now compare values and how you can convert values, type coercion, and what the comparison means in JavaScript, which is this fancy words that is the referential equality, and what are the algorithms that govern this. For example, is a double equal or the triple equal, and what is doing behind the scene, and also is the places where we can now coerce or where our values are coerced or convert, whether it's the if or in a while statement, for example. And how can also organize our code in our programs, whether it's a function or a class or as an EX6 model. And then on the model 3, we dive deep into this nuance of the languages or the low level features of the language that virtually affect every line of code in that say, hey, there's some several topics here. One of them is the iteration. Why we need to care, why do we even care about this iteration? And why now developers through the entire industry say, well, we have now these particular patterns when you have now problems related to creating. Oh my god. And holy hell. All right, here we are. Um, so yeah, this particularly, so the particular patterns. So for example, when do we need to create objects? All right. So what are this particular way of doing that? And I'm describing is this because this has shown now recurring. So there are recurring problems in our code, in our programs, especially when the problem is about cooperation. So we use now the object programming to do that and say, hey, anytime that we need to create an object, all right, that we want to cooperate with others, we have now these particular patterns. So again, this design patterns is just common solutions to common problems. Okay, so this is the creational pattern. The other is the structural patterns. When we care about is that how we going to extend or how we going to assemble different uh, objects into a large structure that can be easy to maintain. This is part of the creational patterns, right? uh, Such as the adapter or the bridge or the facade, uh, the pro, the proxy as well. Again, this is something that I remember, and also is the um, concern about the algorithm in itself and its responsibility here, right? So for example, is that how do we iterate through a collections of values? So we have now the iterator pattern. How now we listen for a particular event, or we look for us for a value and change that value. And anytime that it changes, we want us to be notified from that. So we have is the observer, for example. And this is just to mention is some of these couple. This is this design here, behavioral, right? I am quite familiar with the iterator and the observer, all right? And I do not want to get into that because that's not what this video is all about. But I just wanted to point that out that because this particularly low level features, which is now virtually affect every line of code, which is part of this chapter 3 in order to going from the more general into now the root of the JavaScript. So this aspect, like iteration, is one of them that is relevant in the language because it now implements this iterator patterns that expose now is a method that has an underlying reference to the huge data source, that anytime that we call this method called next, we get the value out of this, right? So this is part of the iterator protocol. And yesterday we make a particular example of how can we now create is or how can we implement is the iterator protocol in collections that they don't have that. For example, objects, all right? Uh, and also is the iterables as well, which is the collections of where we can now iterate over. What are the collections that we can do that, or we can use in JavaScript? And also is two pervasive concepts that are important for us to understand and to be competent in JavaScript, like closures, this, and object prototype. So this the closure, which is a way of how a functions remember uh, and continue to have access to variables from the outer scope in the inner scope, and because this is something that is governed by the scope, and this scope is a set of rules, or is the scope defined is how now variables and it is referenced are resolved. You can think of this like some sort of table that is now attached to that function that has this reference. In other words, it's a reference of all of these variables that are gonna be carry over uh, across your programs. Anytime that you do is a closure. So this is important because another feature of the function, which is that this is part of the anatomy of the function, is a closure, and the other is the this, which is how you can now access to this variable at runtime called the execution context via the this keyword. That you can modify that value, or this value has something by default, all right? And this keyword, which is determined by how you call that function, you can not only have access to that particular data, but you can, as I mentioned before, you can modify that data. I also look at an example of how can you do that, especially with functions, which is this is the feature of functions, all right? Like using the call and bind and call. Uh, and then the feature from object is that uh, in order to figuring out if a particular object has a property, all right, uh, which is this resolution property access mechanism, this is what the object prototype is. And the object prototype is just a reference, it's just a way of how now two different objects can collaborate with each other, all right, in order to resolve is or for property access resolutions. So if object B from object A, when you look up for a property in object B, it doesn't have, it's not there, then through this change, or the prototype change, it's going to now look up and delegate that lookup to the object A if that exists. If not, it's gonna throw an error. So the way of how we can create this reference here is using the object of create. All right, and this is might be quite interesting topics because again we are now combining is the object dot the collaboration aspect. When we are combining is two problem here. When you need computational calculations to do that, we use now the functional programming. And when you need cooperation and collaboration among different objects to figuring out if they have that particular data or it is functionality, we use now the object-oriented programming, particularly using the prototype change in the case of JavaScript. So this understanding of the language, as well as how can we now combine is that this keyword in order to yeah, how can we combine is the this keyword with the object with the prototype change, all right. uh, when we know that, right, in doing so, we can now is not only have the ability to extend the functionality of our program at runtime, okay, uh, and therefore now, well, have that ability that is needed in any program and also in our life. You can just apply this to your life if you want to. That go beyond the scope of today's video, but I do want is to now deep dive into what a scope is, right? Which is this the second edition of the You Don't Know series yet, right? Scope and closures, the second edition. So in chapter one, so here is describing is so what is scope, which is one of the most fundamental, yeah, the most fundamental things in our program is working with variables. Remember, variables are containers of data, of values that represent something. And because of this series of relationship, okay, that this value can represent is something, and this value can be held inside of a variable. This relationship, and a good example of that to be more concrete, is that that's going to use a particular format to represent dates as a value string that we're gonna held in a container, a variable, and anytime that we need that, all right, we just only call that reference. This is one of the reasons why it is important to go with the variables in itself, or to understand now variables. And there's a couple of questions here that how now JavaScript knows which variables can have access at a particular statement, and the other is that how JavaScript knows how JavaScript handles is when two variables has the same name, all right. So all of this is governed by this scope, a well-defined rule called a scope. And this book will go through all the aspects of a scope and how it works and what is useful for and gotchas to avoid. So my question is does ECMAScript actually talk about the scope here? Let me take a look at this. Scope. Scope and the standard defines the ECMAScript general purpose programming language, but scope analysis. The syntax directed operation. This syntax directed operation are consists of algorithm. So anytime you look at the word operation is an algorithm, okay? If each of which is associated with one or more production from one of the ECMAScript grammar. Okay. Okay. So it defines algorithm that produce now JavaScript grammar. One or more productions of ECMAScript grammar. But again, this is the syntax operations. All right. Exactly. Syntax operations. So in this case, the static semantics bound names is this algorithm that produces this grammar, one or multiple ECMAScript grammar, static semantics, and scope analysis. Interesting. Syntax directed operations, whether it's evaluation, okay, whether it's a scope analysis, whether it's labels, contains duplicate label, whether it's function names inference. Function names inference has name is function's definition. Oh, okay, syntax directed operations. Uh-huh. Okay. So this, in addition to those defined in this section, specialized syntax-directed operations are defined throughout this spec. So it says a syntax-directed operation is a name operation whose definition consists of algorithm of each of which is associated with one or more productions from one of the ECMAScript grammar. A production that has multiple alternative definitions will typically have a distinct algorithm for each alternative. So when an algorithm is associated with a grammar production, it may reference the terminal and non-terminal symbols of the production alternative as if they were parameters of the algorithm. When used in this manner, non-terminal symbols refers to the actual alternative definition that is matched when parsing the source text. The source text matched by a grammar production or parse node derived from it is the portion of the source text that start at the beginning of the first terminal that participate in the match that ends at the end of the last terminal that participate in the match. When an algorithm is associated with a production alternative, okay, the source text matched by a grammar production. But when an algorithm is associated with a production alternative, the alternative is typically shown without any this grammar annotations. Such annotations should be only affected by syntactic recognition, or the alternative has no effect on the associated semantic for the alternative. Syntax-directed operations are invoked with a parse node and optionally other parameters by using the convention on step 1, 3, and 4 in the following algorithm. Syntax operations are invoked with a parse node, and a parse node the syntactic grammar. Which is something we're gonna talk about parse node. Okay, when a parse is successful, is construct a parse tree, which is part of the abstract syntax tree, a rooted tree structure in which each node is a parse node. Each parse node is an instance of a symbol in the grammar. It represents a span of the source text that can be derived from that symbol. The root node of the parse tree, representing the whole of the source text, is an instance of the parse goal symbols. When a parse node is an instance of a non-terminal, so it's describing is what we're going to talk in this video. All right, okay, that's quite interesting. The syntactic grammar for ECMAScript is given in clause 13. ECMAScript expression and identifiers through 16. Script and models here. And parse script. This grammar has ECMAScript tokens defined by the lexical grammar, and it is terminal symbols. The lexical and regular expression here. It defines a set of production starting from two alternative goal symbols, script, and models that describe how sequence of tokens form syntactically correct independent components of ECMAScript programs. So when a string of code point is to be parsed as an ECMAScript script or model, it is first converted to a string of inputs element by repeated application of the lexical grammar. This string of input is then parsed by a single application of the syntactic grammar. The input string is syntactically in error if the string of the input elements cannot be parsed as a single instance of a goal non-terminal script or model. But here is describing this. When a parse is successful, it constructs a parse tree. This is exactly the place where it tells you this, right? So this is what the language in itself is actually telling what it's doing. So when a parse is successful, it constructs a parse tree, a rooted tree structure in which each node is parse node. Each parse node is an instance of a symbol in the grammar. It's an instance of the symbol in the grammar. All right. So this grammar, you can think of this like a table. You can think of this like a dictionary. All right. That has all of these different symbols or definitions associated, right? It represents an span of a short text that can be derived from that symbol. The root node of the parse tree, representing the whole of the source text, is an instance of the parse goal symbols. When a parse representing the whole source text is an instance of a parse goal symbol. When a parse node is an instance of a non-terminal, is also this. So new parse nodes are instantiated for each invocation of the parse, and new array used between parse even of identical source text. Parse nodes are considered the same parse node if and only if they represent the same span of source text, are instances of the same grammar symbol, and result from the same parse invocation. So parsing the same string multiple lines will lead to different parse nodes. For example, consider this. Each call of the eval converts the value of the string into ECMAScript source text. Into ECMAScript source text. Okay. And perform an independent parse that create its own separate tree of parse nodes. Okay. It creates own separate tree of parse node. The trees are distinct even though each parse operates upon a source text that was derived from the same string. So in other words, it creates now different. So it create now different parse here. Parse node are specification artifacts, and implementations are not required to use an analogous data structure. Okay. But again, we know now for sure of what this actually is telling that what's going on. So when a parse is successful, it constructs a parse tree, a rooted tree structure in which each node is a parse node. This is telling you now what is going on here, which is aligns to what is describing here. And also, this is a reason why I want to make the reference of this spec, because it's all about here. It all's here. Syntax directed operations, which is our algorithm that produce now ECMAScript grammars. ECMAScript grammars. ECMAScript grammar. ECMAScript grammars. So this scope analysis, which is part of the syntax directed operation, is that. So the syntax directed operation, which is this algorithm that produce now ECMAScript grammars, bound names takes no argument and return a list of strings. Default. It is used within the specification as synthetic name of the model default export when it does not have another name. An entry in the model's environment is created with that name and hold the corresponding value, and resolving the export name default by calling resolve export. For the model will return a resolve binding record whose binding name is default, which will then resolve in model's environment to the above mentioned value. And this is done only for ease of a specification, so that anonymous default export can be resolved like any other export. This default string is never accessible to ECMAScript code or to the model linking algorithm. Okay, or to the model linking algorithm. So here's the finding is this. Okay, here's the finding is the scope analysis. Bound names, binding an identifier returns a list of sole elements here. Binding identifier, it can be either a identifier that is not a reserved keyword. It can be yield. It can be an await. It can be a lexical declaration, let or count. It can be a binding list followed by a lexical binding. It can be a binding identifier, an initializer. An initializer. So it's like an assignment expression here. An initializer that can be in, yield, and await, followed by this. An initializer. In, yield, and await. Okay, an initializer, which can be is equal to any assignment expression. So for example, in this case, it can be binding identifier, any of these binding identifiers, identifier, yield, and await, followed by an initializer. It can be a binding pattern, and this binding pattern can be either as an object binding pattern. Okay, an object binding pattern, or even a REST property or property list. Okay, or binding property list, and binding REST property, binding property list, and binding REST property. Binding list, and lexical binding. Let names once be the bound names of binding lists. Let's name 2 be the bound names of okay, this is not describing is this. Binding list that it can be is either it's a binding where we are. Binding pattern. Whether it's an object binding pattern or an array binding pattern, which is either an elision, optional, elision. They call that as like that, okay. An elision and the binding REST element or binding element list and so on. What's the other one? Exactly, binding list and lexical binding, binding identifier and initializer, and binding pattern and initializer. Binding patterns here, whether it's an object or an array. Okay, variable declaration list. Variable declaration list, variable declaration, binding identifier or binding pattern, and the object binding pattern is actually telling you this. Object binding pattern like this, array binding patterns, all right, and binding property lists, and return a list concatenation of name ones and names 2. Binding property list, binding element list, and all of this for and let or declaration for, in functions declaration. Exactly, this is bound names. Whether it can be either as a binding identifier, Okay, and this identifier can be is this. All right, is binding the identifier, whether it's an identifier or any of the reserved keyword, a lexical declaration, or a variable declaration, or even an object declaration, or an object binding, an array binding, an array binding property list, binding, single name binding, for declarations, functions declarations, functions declaration here, whether it's have a binding or not, and the formal parameter return a new empty list, and the formal parameter here, which is functions rest parameter here, formal parameters. Oh, as a parameter as well, as a parameter that is going to live inside of a function or a class. Formal parameter, arrow parameter, arrow functions. Generator declaration, async generators, class declarations, async functions declaration, cover call expression, then async arrowhead, import declarations, import list, name import list, and export declaration as well. All of this is just to describe is this scope analysis. Holy hell. Then the declaration part. So the syntax operation declaration part, which is an algorithm, remember the syntax operations declaration part takes no arguments and return a parse node. It is defined piecewise over the following production. Hostable declarations, whether it's functions, generator, async functions, class, and lexical declaration. Declaration part. Okay, the other is constant declaration, static semantics. Is constant declaration. Okay, and the lexically declare names. Lexically declare names. Lexically declare names. Lexically scope declarations. And here's where it tells you this. Lexically scope declarations. Another syntax directed operation. Var declare names. Var scope declarations. Top level lexically declare names. Top level var declare names. Top level var scope declarations. But here is telling you now this scope analysis here. Okay, let's go to read about this. Let's go to read about this. Yeah, let's take a let's read about this. Okay. Holy moly. Okay. So our focus will be first of the three pillars in JavaScript, the scope system, which is what we are actually reading about this. The scope analysis or the scope system, and it is function closure as well as the power of the model design pattern. JavaScript is typically classified as an interpreted scripting language, so it is assumed by most that JavaScript programs are processed in a single top-down pass. But JavaScript is in fact parsed, compiled in a separate phase before execution begins, because it's actually telling that. The code author decision on where to place variables, functions, and blocks with respect to each other are analyzed according to the rules of a scope. The scope analysis. So the way how you now put these variables, functions, imports, exports. Exactly. The place where you put now your variables, functions, import and export, and blocks with respect to each other are analyzed according to the rules of a scope during the initial parsing and compilation phase. And this parsing phase happens is at the abstract operation, is the scope analysis here. The syntax directed operations. So the code author decisions on where to place these variables, functions, and blocks with respect of each other are analyzed according to the rules of a scope during the initial parsing and compilation phase. The resulting scope structure is generally unaffected by runtime conditions. JavaScript functions are themselves first-class value, and they can be assigned and passed around just like numbers or a string. So exactly. So since here we are looking is at the JavaScript is typically classified as an interpreted scripting language, so it is assumed that most JavaScript programs are processed in a single top-down. But in fact, JavaScript parse and compile in a separate phase before it executed. Okay, so the code author decisions of where to place the functions, the block, and the variables with respect of each other, they are analyzed by the scope system. All right. So during the initial parsing phase, which the result scope structure are not affected by runtime's conditions. So JavaScript, since JavaScript treats functions as values, and if we can assign or pass just like a number on a strings, since these functions hold and access variables, so they maintain the original scope no matter where in the program these functions are eventually executed. And this is called closure. You see, closure is something that happens at scope time, or before the code is executed in this parsing phase, that is going to now determine is the relationship of these functions variables, of these functions variables, of the functions variable and blocks, how they relate each other. Okay, and all of this now analyzed is at parse time via the scope system, or with the scope rules, right? That is happening exactly. So because of this happen, this is just okay. All right. So because JavaScript is So because JavaScript is typically classified as an interpreted language, we can think that all of our JavaScript programs are going to process now from single top and down. But in fact, is that JavaScript doesn't behave that way. In fact, it has now a parse or compile phase before your code is executed. So the co-author decisions of where to put now variables, functions, and block respect to each other's, they are analyzed by the set of scope rules during the initial parsing and compilation phase. So the result, exactly. So the result of that scope structures are not affected by runtime's conditions. And because now functions in JavaScript are values and pretty much like strings and numbers that we can pass those values, functions that held variables reference or that hold and access variables, they maintain the original scope. They maintain the original scope no matter in which part of the code that function is being executed. And this is called now closures. So models are co-organization pattern characterized by public methods that have privileged access via closures to hidden variables and function in its internal scope of the models. So here we're talking about is the compile versus interpreting. Okay, you may have heard a code compilation before, but perhaps it seems like a mixed black box where source code slide in one end and the executable programs pop up the other. It is not a mystical or magical, though. Code compilation is a set of steps that process the text of your code and turn it into a list of instructions that the computer can understand. So typically the whole source code, this code compilation, is transformed at once. And those resulting instructions are saved as output, usually in a file that can be later be executed. You also may have heard that code can be interpreted. So how it is that different from being compiled? So interpretation performs similar tasks to compilation. So in that it transforms your program into machine understandable instruction, but the processing model is different. So unlike a program being compiled all at once, okay, which is a set of steps that process your text, exactly, it's a set of steps that process your source of text into instruction that can be executed by the computer. But the processing model is different. Unlike a program being compiled all at once, with one interpretation, the source code is transformed line by line. So each line of a statement is executed before immediately proceeding the processing of the next line of the source code. Yes. So as the illustration of this happens, right? So are these two processing models mutually exclusive? No, right now, but generally yes. However, the issue is more nuanced because interpretation can actually take other forms than just operating line by line on source code text. Modern JavaScript engines actually employ numerous variations of both compilation and interpretation in the handling of JavaScript programs. Recall that we surveyed this topic in chapter 1. Exactly. Our conclusion that is that JavaScript is most accurately portrayed as a compiled language. For the benefit of the reader, here for this following section we'll revisit and expand on that assertion. Compiling code. But first, what does it even matter whether JavaScript is compiled or not? Scope is primarily determined during compilation. So understanding how compilations and execution relate is the key in mastering a scope. hmm So how compilation and execution relate is key to understand the scope. In classic compiler theory, a program is processed by a compiler in three basic stages: tokenizing and lexing. Okay, a program is tokenizing and lexing, breaking up a string of characters into meaningful to the language chunks called tokens. For instance, consider the program var a equal to. This program will likely be broken up into the following token. Exactly, uh, into this token. Whitespace may and may not be persisting as token depending on whether it's meaningful or not. The difference between tokenization and lexing is subtle and academic, but it centers on whether or not these tokens are identified in a stateless or stateful way, if that token contains that particular state. Put it simple, if the tokenizer were to invoke stateful parsing rules to figure out whether A should be considered a distinct token or just part of another token. That will be lexing. But it will be lexing if just to consider if they are exactly. That will be lexing to just part of another token, a distinct token, so or just part of another token, or should be considered a distinct token. So if the tokenizer were to invoke stateful, and is the tokenizer, if if the tokenizer were to invoke stateful, okay, if the tokenizer were to invoke stateful parsing rules, okay, hey, is that particular rules contains now a state or describe now a state, it is lexing. Lexing, what how do you translate lexing? Semantically or syntactically. Lexical analysis is a conversion of a text into semantically or syntactically meaningful lexical tokens belonging to categories defined by a lexer program. In the case of the natural language, those categories include nouns, verbs, and adjectives, punctuation, etc. In the case of programming language, the category includes identifiers, operators, grouping symbols, data types, and language keyword. Lexical tokenization is related to the type of tokenization used in large language models. Exactly. Lexical tokenization is related to the type of tokenization used in large language model, but with two different. First, lexical tokenization is usually based on lexical grammar, whereas LLM tokenizers are usually probability based. So first, lexical tokenizer is usually based on lexical grammar. Holy hell, okay. In a well-defined grammar, whereas LLM tokenizers are usually probabilistic based. It's a lexical grammar of probabilities. Holy shit. Second, this is what the lexical tokenizer is usually based on. This is what this this is what this is based on. First, lexical tokenization is usually based on the lexical grammar, whereas LLM tokenizers are used probability based. Second, LLM tokenizers perform a second step that converts a token into numerical values. Okay. So now that it received this token and the tokenization passed through a probability lexical grammar, hey, what is the probability of this word? And then it's going to now convert that token into a numerical values, rule-based programs. Mhm. This is something that relates a lot here. Okay. So lexical analysis. Okay. This is talking about is compiling code or transform your code or transform a source of text. Interesting. Transform a source of text into something, um, yeah, transform a source of text into a, yeah, transform a source of text into, uh, transform your source of text into something that can be understood by the machine. All right. Hmm. So in the case of JavaScript, this phase in which now the compilation in traditional or in classic compiler theory, this series of a step is made of the tokenizer and lexing, the other is the parsing, and the other is the code generation. Hmm. And turning into executable code here. So this part vary greatly depending on the language, the platform is targeting, and other factors here. Hmm. So these three phases, all right, are the phases in which um, the code is transformed into something that can be understood by a program. Why this is important to understand? Because if we know, um, if we know, if we know how this, if we know how this process work, makes some. If we know how this process work, um, and since we're looking at scope, we can mastering is this topic, and therefore our understanding of uh, concepts like closures and how we can now organize our code in this modular way using closures. Hmm. But also, is it tokenizing here? So, but the difference between tokenizing and lexing is that if the tokenizer were to invoke stateful parsing rules to figuring out whether A should be considered a distinct token or just part of another token. But this is now hints to the tokenizer. Hey, tokenizer. Uh, if this particular token here has some state that needs to, if this token, exactly, if we're invoking this stateful parsing rules to figuring out if this particular token should be considered a distinct token or just part of another token. This is the tokenizing and lexing. And then once you tokenize all of this, which is the process of breaking up uh, your source. Okay, it's the process of breaking up your source code into tokens, right? Now that it has this token, this strings of token, let's going to transform that into a tree-nested element. Uh, that represents the grammatical structure of the program. This is called the abstract syntax tree. They don't mention this because, again, this is now an spec. It doesn't tell you what to do. Again, it doesn't go into the implementation details. It tells you how things should be or must be. Okay, so for example, the tree for var a and 2 might start with a top level node called variable declaration with a child node called identifier whose value is a and another child called assignment expression which itself has a child called numeric literal whose value is 2. code generation, taking an abstract syntax tree and turning into executable code, and this part varies greatly depending on the language. But this is now the phase, and now it makes a lot of sense. But this is now the phase on classical compiler theory described to transform source text into code that can be understood by the machine. So you need to transform, you need to identify all of these tokens, or you need to pass through the tokenization here. It's going to break up your statement of your program into tokens. Then it's going to construct now a structure that represents the grammatical structure of that code, of that instruction that you, of that source of text, and build the abstract syntax tree, and then it's going to generate is the AS, and then it's going to generate is the code here in code generation. So the implementation detail of a JavaScript engine utilizing memory, system memory resource, etc., is much deeper than we'll dig here, and we'll keep our focus on the observable behavior of our program and let JavaScript engine manage those deeper system level abstraction. The JavaScript engine is vastly more complex than just these three stages. In the process of parsing and code generation, there are steps to optimize the performance of the execution. It collapsing redundant elements. In fact, code can be even recompiled. In the JavaScript engine is vastly more complex than just this three stage. In the process of parsing and code generation, there are steps to optimize the performance of the execution. Besides that, there are now between these different phases. All right. Also, it's gonna be a JavaScript engine implementation base to say, hey, not only that we need to transform is this source of text into machine readable code, but also is we need to do some optimizations along these phases here. So this optimization that you can do, we need to do some optimizations here. So if you're preparing a meal, all right, you have all of these ingredients, and then you want a desired output, a particular cake, or no, asado. I really love this. So you're gonna transform all of these ingredients into an asadito, all right, a roast beef, okay. So, and also you want us to now, in the middle, optimize stuff. So, for example, like how much fire you're gonna put in. So, for example, is how much coil do you need to make the barbecue? What is the specific ingredients that you need to? How much water do you need to? Do you have everything in place, or do you need to actually set everything to make that asadito, for example, to make that barbecue? Okay. Okay. Interesting. So I'm painting only with broad stroke here, but you will see shortly why this detail we do cover, even at a high level, are relevant. JavaScript engine don't have the luxury of abundance of time to perform their work and optimization, because JavaScript compilation doesn't happen in a build step ahead of time. As with other languages, it usually must happen in mere microseconds or less, right before the code is executed. To ensure the fastest performance under this constraint, JavaScript engine use all kind of tricks. So just-in-time compilation, which lazy compile and even hot recompile. So it's like compile that language into something that can be and then recompile that again to have everything there. These are well beyond the scope of our discussion. Well beyond the scope of our discussion here. Require two-phase. To state it is as simple as possible, the most important observation we can make about processing of JavaScript program is that it occurs in at least two phases. Parsing, compilation first, and then execution. And during this parsing and compilation is where now these optimizations needs to happen, because JavaScript in itself doesn't have any build time like in any other languages, right? Or a build step. So this needs to happen is at mere microseconds. Why is this? Because the dynamic nature of the language, because the dynamic nature of the web. This is why this has been so powerful. And don't get me wrong, because if you want to now run synchronous stuff, or if you want to have much more fine control over your assets management or your resource management, so C, C++ or Rust can be much more adequate for the task. Interesting. And the separation of a parsing compilation phase from the subsequent execution phase is observable fact, not theory or opinion. Exactly. You can take a look at the specification. While the JavaScript specification does not require compilation explicitly, it requires behavior that is essentially only practical with a compile then execute approach. These are three programs characteristics that you can observe to prove this to yourself: syntax errors, early errors, and hoisting. And this is now our features that shows that the behavior of JavaScript act like a compiled language, or that this parsing phase, and it's because of how now syntax errors are handled. Early errors, as well as what, for example, in the case of functions, okay? Early errors, all right? And the other is hoisting. And the other is hoisting. So for example, is this. It's a early errors and use a strict, for example, early errors. There's another early errors as well that happen, but I think this is the most significant one. Early errors, and the other is hoisting. So hoisting is now is a feature of the language that happened that indicate that JavaScript is now it has now two phases: the parsing and the compilation, where is now transformed the source text into stuff that can be understood by the machine. Okay, and in a classical compiler theory, you have is now the tokenizing or the lexing, the parsing, and then the code generation, right? And then the code generation. But because now JavaScript doesn't have any build step like any other programming or compiler language, So it needs to analyze this code at microseconds, or even less, to do that. So in order to understand now that JavaScript is in fact a parsing or compiled language, but it's based on its features of how now it, based on the characteristic of the language, okay, when it comes to analyze syntax errors. So to prove yourself is that, for example, syntax errors, early errors, and hoisting. And in the case of hosting is because of this. So we define now this particular function, say something here, var greetings equals to hello, all right? And then you define now a block, the scope here, you define another scope here, and say, I want to now use greeting and say howdy, so assign these variables to this, and then now define is this greeting here with the value of hi, and then now console log is the greeting here, and then you say something. Right? What happened here is that because now these three features of the language that these three features of the language that show is now that JavaScript is a compiled language, or a parsing compiled language, not an interpreted language as we might think, okay? But it's one of them is for syntax error, behavior. And it's because now we are looking is at the implementation, not at the spec. Well, the spec says something, but also is that how this is implemented. So it's based on its syntax error, based on how it analyzes syntax errors, how it also throw now as early errors, and then now how it analyzes the scope here, or hosting. So if you are having a reference here, but if you define now this inside of this particular scope, right? The JavaScript engine in itself, it say, hey, you are defining is now this new identifier that doesn't have any reference to that. You can even do something like this, and therefore this will work. So far so good. But if you for some reason now here you are defining now inside of this scope the same identifiers, okay, how now it resolves the same name identifiers, it will now look at the scope rules to do so and say, hey, yes you can, or yes you don't. Cannot access greeting before initialization. Reference errors. The noted reference errors occur when the line with the statements greeting howdy, greetings howdy, and it is at line 5. 1, 2, 3, 4, 5 is say this. It say cannot have access greeting before initialization. So what's happening is that the greeting variable for that statements belongs to the declaration of the next line, let greet, rather than the previous var greeting hello. The only way JavaScript engine could know about this line where the error is thrown is that the next statement will declare a block scope variable on the same name. So it's that now JavaScript somehow knows that reference, know that variable reference, know that how variables and reference are resolved here. So if the JavaScript engine had already processed this code in an early pass and already set up all the scope and their variable associations. So the only way that the JavaScript engine could know at the line where the error is thrown that the next statement will declare a block scope variable on the same name. Greeting if this is the JavaScript engine and has already processed this code in an early pass and already set up all the scope and their variables association. This processing of a scope and declarations can only accurately be accomplished by parsing the program before execution. The reference errors here technically come from greeting howdy, accessing a variable too early, and a conflict referred as the temporal dead sum. Chapter 5 will cover more in detail. It is often asserted that Latin const declarations are not hoisted, but that's not accurate. We'll come back and explain about that. Hopefully you're now convinced that JavaScript programs are parsed before any execution begins. But does it prove they are compiled? This is interesting question to ponder. Could JavaScript parse a program but then execute the program by interpreting operations represented in the AST without first compiling the program? Yes, that is possible, but it's extremely unlikely, mostly because it will be extremely inefficient performance-wise. It is hard to imagine a production quality JavaScript engine going all the trouble of parsing a program into an extra syntax tree, but not the converting, aka compiling. Exactly, we can think of that, that a JavaScript program, it is possible for a JavaScript program to parse and then execute the program by interpreting operations representing in the AST. Yes, it is, but it's not that efficient. Many have endeavored to split hair with this terminology, and there is a plenty of new and well, actually, interjections floating around. But in speeding and in practice, what the engine is doing is processing JavaScript programming in a much more alike compilation than not. Classifying JavaScript as a compiled language is not a concern with the distribution model. And how the program is distributed, for it is binary or bytecode executive representation, but rather in keeping a clear distinction in our mind about that the phase where JavaScript code is processed and analyzed. This phase observably and indisputably happens before the code starts and executed. So the idea of having this mindset, the idea of classifying JavaScript as a compiled language is not in terms of how in the distribution model, but in how JavaScript analyze and process the code based on what is observable. And then the compiler speak with awareness of the two-phase processing based on this characteristic, how it analyzes syntax error, early errors, and hoisting. Let's turn our attention on how JavaScript engine identifies variables that determine the scope of a program and it is compiled. First, let's examine a single JavaScript program to use for analysis over the next several chapters. Like this. Alright, so here we have is now a collection, an object that is assigned to a student identifier that is held inside of a variable. And the same for function, and the same for other than declarations, all occurrence and variables identifiers in a program serve in one of the two roles. All occurrence of variables identifiers in the programs serve to two roles. Either they are the target of an assignment or they are the source of a variable. When I first learned compiler theory while earning my computer science degree, we were taught the term LHAs, aka target, and RHS, aka source. For this role, respectively, as you might guess, the L and the R, the acronym mean left-hand side and right-hand side. However, assignment targets and source don't always literally appear on the left or on the right. So it's probably clear to think in terms of the target and source rather than the left and right. How do you know if a variable is a target of an assignment? How do we know if a target, if an assignment, or the source? Okay. Well, check if the value that is being assigned to. Check if there is a value that is being assigned to. So that becomes now a variable. Or that identifier or variable has become is the target. Why this is important? It is a target. If not, then the variable is a source. For the JavaScript engine to properly handle the program variables, it must first label each occurrence of a variable as a target or source. And we'll dig in now to how each role is determined. What makes a variable a target? Consider this. This statement is clearly an assignment operation. Remember, the var student part is handled entirely as a declaration at compile time, and thus is irrelevant during execution. We left it out for clarity and focus. Same with the next student get student name statement. But there are other target assignments operations in the code that happens perhaps less obvious. Target assignments here. Okay, exactly. Target assignment. This is the most obvious. This is another that to me was not that obvious. And this is another one. But again, why this is important to know if a variable is a target or a source of a is a variable is a target of a source of an assignment. But how is that an assignment to target? Look closely at this. The statement assigned to variable for each iteration of the loops is another target reference. And get student name here is a target reference because you are assigning that. But how is that is an assignment target? Look closely. The argument 73 is assigned to the parameter student ID. And there is one last, okay. So this is assignments here. As a variables, as a function, as a student from the for loop, okay, and the other is as the value that we're passing to this. So this is another source target or target assignment here. Okay, a function declaration is a special case of a target reference. So you can think of it's sort of like var get student equals name, but that's not exactly accurate. An identifier get student name is declared at compile time, but the equality function student ID part is also handled at compilation. The association between get student name or the function is automatically set up the beginning of the scope rather than waiting for an assignment statement to be executed. The automatic association of a function and variable is referred to as function hosting. The automatic association, okay, this is what we are looking at this. At the assignments of variables. the assignment of variables and the target in here. This automatic association of functions and variables refers to as function hoisting and is covered in detail in chapter 5. But the association of a function and variable is referred as that. So we have identified all 5 targets referenced in the programs. The other variable reference must then be source reference, because that's the only other option. In for let student of a student, we say that student is a target. In for let student of student, we say that student is a target, but student is a source reference. In the if, the student ID and the student both are reference. Or sources, exactly. Are source reference. So student is also a source. So student is also so student is a target here in this statement. Student ID and the student ID, both of them are source reference. And the student.name, what is returned, is a source reference. In get student name, the get student name is a source reference, whereas 73 is an assignment here, where the value okay, it is because you are talking about here is the source reference when the assignments happen here. And if the assignments happen here is this. So console is a source reference as is next student. In case you were wondering, ID, name, and log, all properties, and log are all properties, not variables reference. What's the practical importance of understanding target versus sources? That's a good question. In chapter 2, we'll revisit this topic and cover how variables and roles impact its lookup. How variables role impact its lookup, specifically if the lookup fails. Cheating runtimes modifications here. And then you look at this cheating runtime modification scope. This is a bad idea. Yep. And lexical scope. We have demonstrated that JavaScript code is determined at compile time. The term for this kind of scope is lexical scope, and lexical is associated with the lexing stage of compilation, as discussed early in this chapter. To narrow this chapter down to a useful conclusion, the key idea of lexical scope is that it is controlled entirely by the placement of a function, blocks, and variables declaration in relation to one another. If you place a variable declaration inside of a function, the compiler handles this declaration as it is parsing the function. And associated that declaration with the function scope, If a block scope declare let comes, then the association with the nearest enclosing block rather than it is enclosing function as with var. Furthermore, a reference target or source roles for a variable must be resolved as coming from one of the scope that are lexically available to it. Otherwise, the variable is stated to be undeclared, which usually results in an error. If the variable is not declared in the current scope, the next outer enclosing scope will be consulted. The next outer enclosing scope will be consulting. In this process of stepping out of one level of a scope, nesting continue until either a matching variable declaration can be found, or the global scope is reached and there is nowhere else to go. It is important to note that compilation doesn't actually do anything in terms of reserving memory for scope and variables. Reserving memory for scope and variables. None of the program has been executed yet. Instead, compilation creates a map of all the lexical scope that lays out of what the program will need while it executes. You can think of this plan as insert code for use at runtime, which define all scope and register all the identifier variables. In other words, while scopes are identified during compilations, they are not actually created until runtime. Each time a scope needs to run, in the next chapter we'll sketch out the conceptual foundation for lexical scope. And that'll be all for this video. Take care. Bye bye.